Hello everyone. Today, or right now, or wherever you're watching this, we are going to do the Unit 7 exam multiple choice. Unit 7, equilibrium. 14 multiple choice questions. Let's go ahead and get into it. All right. That looks good. That looks good. All right, right before. All right, shown above is the chemical equation for the dissolution of slightly soluble. Let's make myself a little smaller here. Slightly soluble salt, copper 2 or copper 1 bromide. The KSP value in pure water was experimentally determined. Copper bromide is found to be much less soluble in 0.001 molar sodium bromide than in pure water. Now I cut it off a little bit. Which of the following correctly explains why the decrease in solubility for copper bromide in the 0.001 molar solution of sodium bromide? So this is the common ion effect. This is just saying if we dissolve this salt that has bromide in it into a solution that already has bromide in it, then it's not going to dissolve as much. So which of this says that? The presence of additional bromide already in the solution decreases the value of KSP. That's not true, because the presence of the bromide doesn't do anything with KSP, but it does change the solubility. The presence of additional copper bromide ions already in the solution means equilibrium will be reached when much less copper bromide has dissolved. That is true. Remember when we did Rice table with these, the thing that we're changing when we do common and ion effect is now we have 0.001 of this. But we don't actually change the KSP. That KSP only changes with changing temperature. Na has nothing to do with it. The concentration of water is much less in the sodium bromide solution than in pure water, reducing the rate. That doesn't really make sense either. So the answer is D. Based on the equilibrium constants given, which of the following gives the correct expression for the equilibrium constant for reaction 3? So based off of this, it looks like we're doing the pseudo-Hess's law with equilibrium constants. For our rule for equilibrium constants is if we flip, then we have to do 1 over. If we multiply, we raise to the power, and at the end we multiply everything together. So we need to flip this reaction because I need that OCl in the reactants. So it's going to be 1 over K1. We're not even looking at these at all. So it's going to be 1 over K1. And then we keep reaction 2. We have OH in the products already as we are. Just quick mental check. When we add these together, do we get that? This H2O will cancel out with one of these once we flip that reaction. And the answer is, and then the H3O plus will cancel out once we flip. And the answer is yes, we will get that reaction. So multiplying these K's together, K3 is equal to 1 over K1 times K2, which is K2 over K1, which is A. A cylinder with a movable piston is completely filled with a small amount, 100 millimoles of liquid water at pressure 1 atm at a temperature of 80 degrees Celsius. All the air in the cylinder is excluded. The cylinder is placed in the water bath held at 80 degrees Celsius. The piston is slowly moved out to expand the volume to 20 liters, and we're tracking this pressure. So as we know that when volume goes down, pressure should go up. That's P1 V1 equals P2 V2. So we do see that. We see that as the volume goes down, the pressure begins to climb. But then we reach this portion. I guess I should read what the question is asking. Which of the following most closely indicates with justification the region of the curve where equilibrium is represented? What we're looking for equilibrium when it comes to pressure or concentration is we're looking for where equilibrium or pressure or concentration stops changing. That is our evidence of equilibrium. So we're looking for region B here. Region B, we have reached equilibrium. So that is this one right here. So what that looks like is When we reach B, once we reach that small volume, that is when we are going in between gas and liquid. That is when the concentration has stopped changing. What is the value of the equilibrium constant for this reaction? So the equilibrium constant, this looks like just a straightforward calculation one. Z to the third over x squared times y. Concentration of products raised to the power of their coefficients divided by reactants raised to the power of their coefficients. So we have 4 cubed divided by 2 squared times 0.5. 4 cubed, I need my calculator, it's too much math for my head. 4 power 3, 64. 64 divided by 2 is 32. So the answer to this one is E. All right, we're making good pace here. A reversible reaction is represented by the equation above. The amounts of reactants of products at time 1 are shown on the particle diagram on the left. The particle diagram on the right shows the amounts of reactants and products at time 2. Based on the diagram, what can be inferred about the relative rates of the forward and reverse reaction? All right, particle diagram, let's count these particles. I have 3 x's. I have 4 y2s. And then I have 4 xy's. Over here, I have 1x. I have 3 y2s. And I have 6 xy's. So I can tell that the reaction is progressing this way. We are producing xy's and we're using up x and y2s. So the forward reaction is favored here. The forward reaction is progressing more than the reverse reaction. So it's D. The rate of the forward reaction is greater than the reverse reaction. In 1 molar HCl, HCl is nearly 100% dissociated, as represented by the equation above. Which of the following helps explain why in 0.01 molar HCl, less than 1% of HCN is dissociated? So this is a typo. This is supposed to say HCN. Oops. HCN. So the concentrations don't matter here. We don't care that it's 1 molar or 0.01 molar. The question is asking, why does HCl dissociate completely, but HCN does not dissociate completely? Well, it's because the K of HCl is going to be greater than the K of HCN. They have different equilibrium constants. K is products over reactants. So HCl's K is going to be really high. HCN's K is going to be really, really low. It's that equilibrium constant that tells us how much it actually ends up dissolving. So the answer is C. We don't know anything about the CN ion being soluble in water. This doesn't really make sense with what the question is asking. Concentration doesn't really affect the equilibrium constant or the percent dissociation. And then this one's just not true. HCN does not react in water to form a basic solution. Also, that doesn't have anything to do with the dissociation process. All right, the equilibrium reaction between Cl2 and H2O is represented by the chemical equation shown above. And we are given the Kc expression. Which of the following gives the value of the QC and predicts the response of the system immediately after dilution? So we're diluting with distilled water to twice the original volume. So what does that do? Molarity is moles over liters. If we double the volume, if we dilute to get double the volume, well, we're going to have the molarity. If we're dividing by twice as much, well, the molarity is going to go down by a factor of 2. So the molarity, the concentration is going down. So now look what's happening here. And there's a couple different ways to do that. It wants us to think in terms of Q versus K. So let's start off with there. Q is the same expression. If we dilute everything by a factor of 2, then if K is equal to something, let's say, I know that gives us a K, but for the purpose of this, I'm just going to ignore it. Let's say K is, let's say we have a concentration of 2 of everything to begin with. Well, it'll be 2 times 2 times 2 over 2, which is 4. If we have the concentration, Q would be 1 times 1 times 1 over 1, which is 1. Q is 4 times less than K. And since Q is less than K, that means we're going to progress in the forward reaction. They already give us the equilibrium constant expression, so I was just plugging things into there. Another way of thinking about it too is if we dilute, if we decrease the concentration, all of the aqueous solutions are going to go down. And this behaves sort of like the pressure Le Chatelier's trend. If we decrease the concentration of everything, the reaction wants to shift in the way to bring that concentration back up. So the rate of the forward reaction will be greater, and Q is less than K, which is D. The equilibrium system shown above is represented in the diagram below, in which each molecule represents 1 mole of the substance in a 100-liter container at constant temperature. Additional N2O4 is added to the container. Which of the following best represents the system after equilibrium is reestablished? Okay, to help verify equilibrium, I'm going to use a Q versus K check. And I know they give us a K, but I'm just going to make my own K because I know it might not be the right K, but I'm just looking that K matches Q. So let's say that K, the equilibrium constant expression, is the concentration of N2O4 over the concentration of NO2 squared. I'm going to assume each particle is 1 mole and the liter is 1 liter. So for the K, for this, it's going to be 2 over 1 squared, which is equal to 2. I'm going to check that same expression with all of these, and the one that's equal to 2 is going to be the one that's equilibrium. For A, we have 1 N2O4, which is 1 over 3 squared. It's not that one. For the second one, it's going to be 2 over 3 squared, also not that one. For the third one, it's going to be 4 over 2 squared, so 4 over 4, which is 1, so we're getting closer. For the last one, it's going to be 8 over 2 squared, 8 over 4, which is 2. D is the one that is in equilibrium because Q is equal to K. Right. A student mixes dilute silver nitrate with excess sodium chloride to form silver chloride. We know that when silver ions are in the presence of chlorine ions or chloride ions, it's going to form silver chloride. It's going to precipitate out. Which of the following which of the diagrams below best represents the ions that are present in significant concentrations in the solution? So they do give us the KSP for silver chloride, and that's verifying something we already know. We know that when silver chloride is insoluble, it's going to precipitate out. So if we should see silver chloride at the bottom. All of these have silver chloride at the bottom. Let me zoom out a little bit. So next thing we can do to start eliminating things. We're mixing silver nitrate with sodium chloride. And we're said that we're going to have excess sodium chloride. Since silver chloride is the thing precipitating out, and we have excess sodium chloride, that means we're going to run out of silver. This is going to go away first. That's all the silver is going to precipitate out, or nearly all the silver is going to precipitate out. So we shouldn't see silver in our solution at all, which gets rid of D. We could have also gotten rid of B earlier because B only has silver and chloride. Where are the sodiums? Where are the nitrates? They should be in there. So B is also out. All the silver chloride should be in the precipitate. Now, between A and C, the better answer is C. A has the sodium and the nitrate. C has the sodium, the nitrate, and the chloride. We will have extra chloride in there because we have excess sodium chloride, so we're going to have too much chloride for the amount of silver, so we'll see chloride in there as well. According to the information about the dissolution of barium iodate shown above, the correct value of S, molar solubility, can be calculated using which of the following mathematical relationships. We're just going to do a Rice table here. So this is my R. My R is up here, just for time purposes, and my ice is going to be separated from my R. We don't care about the barium iodate, and we're going to start off with 0 concentration of each of these, and then we're going to go plus S, plus 2S, and then E is S, and then 2S. The KSP expression is going to be equal to the barium 2 plus times IO3 minus squared. So we're going to get 4 times 10 to the negative 9th equals S times 2S squared, which is 4S cubed. So 4S cubed equals 4 times 10 to the negative 9th, which is D. I haven't been checking my work along, so hopefully I'm getting them all right. 11. Because pure H2 is a hazardous substance, safer and more cost-effective technique is to store it as a solid for shipping purposes have been developed. One such method is the reaction represented above, which occurs at 200. It's good. You know, this question comes with a fun fact. That's cool. Pure H2 is a hazardous substance. So they ship it as a solid. Who knew? As a solid bonded in an ionic compound. The amount of H2 gas present in the reaction mixture at equilibrium can be maximized. So this seems like a Le Chatelier's question. Which of these things is going to cause the reaction to shift that way? So we're exothermic. Heat is a reactant. If we increase temperature, we're increasing a reactant, and we will get a shift that way. So the answer is, we have temperature and pressure. So we should increase temperature. For pressure, this side has 1 mole of gas. This side has 0 moles of gas. So we should shift it to the left. The way we shift it to the left is we decrease pressure. The rule is if we decrease pressure, it shifts to the sides with more moles. If we increase pressure, it shifts to the side with less moles. We want to decrease pressure to shift to the side with more moles. So the answer there is A. Increasing pressure by decreasing volume. Nope, I was reading the last thing. The answer is B. Increasing the temperature and decreasing the pressure by increasing volume. We want to decrease the pressure, and increasing volume is how we do that. Based on the information above, what is the value of the equilibrium constant for the reaction represented below? This is another like pseudo-Hess's law. How do we get from this reaction to this reaction? It looks like we flip it, and we multiply everything by 2, which for K, that means we do 1 over 0.2, and then we square that. 1 over 0.2 is 5, and then 5 squared is 25, which is D. All right, last 2 questions. Oof. So, downside about not doing the book work this semester is, man, there was a good question in the book that had to do with a graph like this. This is a solubility chart. This is showing us how solubility gets affected by temperature. So just isolating one of these graphs, let's just look at the potassium sulfate. As the temperature goes up, the potassium, the solubility, which is what this axis is measuring, is going up. That checks out with what we know about solubility. As we increase in temperature, we get more soluble. As we increase in temperature, liquids are able to hold more stuff. So solubility generally increases with increasing temperature, but there are some exceptions, as we can see with like this Ce2SO43. Let's see what the question is asking. On the basis of the solubility curve shown above, the greatest percentage of which compound can be recovered by cooling a saturated solution of the compound from 90 degrees Celsius to 30 degrees Celsius? All right, this is a complicated looking graph and a complicated looking question, but this question is really just, can you read a graph that you haven't ever seen before? do you have the ability to interpret a graph that's new to you? We're looking for the line that gives us the greatest change in solid for the change in temperature, 90 to 30 Celsius. So from here to here, which of these graphs change in solubility the most? And the answer is this potassium nitrate. This potassium nitrate goes all the way from up there to right there. The solubility had the greatest change, which means in a saturated solution, if we cool by 60 degrees Celsius, that much solid will be coming out of the solution because it's then oversaturated. So the answer is the potassium nitrate, which is B. Last question of the multiple choice. The solvent in a non-aqueous system represented above is 2-propanol. If a small amount of water is added to the system, how will the color of the solution be affected and why? Hey, I know this reaction. That's our lab reaction. Wow. Let's write a smiley face because something we did on a lab showed up on a test. Okay, if we increase water, there's a little bit of a typo. This should be aqueous. But if we increase water, we are increasing a product, and it shifts to the reactants. So the solution is going to become more pink because we're shifting towards the pink thing and away from the blue thing. So the answer there is A. All right, that is the multiple choice. Let's zoom in on the smiley face with lab. All right, we'll end there for the multiple choice, and I'll get this posted, and then I'll do the FRQ as well. We'll see if I get the FRQ done tonight. I have places to be, but I'll try and get it done before that. But this MCQ will go up once I finish this video, which is now. So anyway, see ya. Bye. Good luck with your studies. Let me know if you have questions. Yeah.